Welcome back. I'm happy you've returned to continue your adventure into derivative rules and tangent lines. Today is more of an extension of day 15 than it is too much new. You'll get a little bit of new stuff, but we're really going to spend a lot of today either focusing on new notation or notation that we talked about last class but didn't really practice, and then one new type of derivative, our e to the x, or exponential functions derivative. So let's get started. We're going to have a quick discussion about Newtonian versus Leibniz notation, and we're going to do it looking at these fun three functions over here. Now, when you first are introduced to function notation, you might forget what each part of that notation is. And in particular, the AP exam is fond of saying something like, let R be a function of x. They'll just give you that part at the beginning. You're like, whoa, how come there's an R and an F? I'm so used to them like being the same letter, or maybe they just tell us that f of x equals x squared. Well, it really depends on who you are, but a lot of people will say that this operator, this f or this g or whatever letter you use here, generally shouldn't be thought of as a variable. So if you have something like, a quick example, let's say if you had y equals x squared, where x is your input, y is your output, some people would frown upon saying, ooh, let's write this in function notation. Let's just say it's y of x equals x squared. They really don't like these two to match, which I think is a little bit silly, but we're going to hold with it because it does happen that way often. So a lot of times you'll have this be your output variable because that's going to depend, it's the dependent variable, on your input, your independent variable. And then somewhere in the middle they'll say that r is a function of x, where this function, technically this letter here, f, isn't actually a variable, right? That's just standing in for all the stuff that's happening to x. This function is telling us that various operations are happening to x. Maybe x is being squared, square rooted, plus 7 divided by the sine of x, something like that. So input, output. Well, why am I going through all of that? Well, I would honestly prefer that almost 100% of the time we just use f as our function notation operator, our f of x. Really use it every single time. However, you can use different variables there, especially when you have like the same input and output variable. It gets confusing if you have f of x. We want to show that maybe it's g of x instead, that there's something else happening. Either way though, how does this relate to calculus? Well, let's get to it. If we wanted to take the derivative of this equation, well, there's a lot going on here. First, let's maybe remember that the Newtonian way doesn't actually have a way to tell you take the derivative. They would just say take the derivative or find the derivative. So if we wanted the derivative of this, there's a couple different ways we could show it. We could say that r prime is equal to, what is the derivative of x squared? I think that's just 2x, right? You could say that f prime of x is equal to 2x. Both of those are fine. Right? You could even say that r prime equals f prime of x, which equals 2x. That's totally okay too. Either one of those is okay. If it's in function notation, we keep the of x. If it's not in function notation, if it's just input output, it's usually written like that. But how does that change with the Leibniz derivative? Well, there's a couple ways to look at this, but I think maybe the most important thing is to realize that to show taking the derivative, we have that dx notation. It means take the derivative. Technically, we read this as take the derivative with respect to x. Now, really, this x right here is whatever the input variable or the independent variable is. So we need to realize that whatever's inside the parentheses, or whatever is on the independent side, has stuff happening to it, has to be the variable at the bottom of our dd whatever, dd input if you want. So if for Leibniz they wanted you to take the derivative, they would say, and I'm just going to do d dx over here of the whole equation, r equals some function of x, which equals x squared, just because I think it's nice to show this way. If you were to write the derivative, right, well, the derivative definitely equals 2x, nothing to do there. It would most commonly be written as dr dx. We usually just take the output and go over here. Leibniz notation doesn't have much to do with function notation. They go about function notation a different way, but sometimes you do see it that way. So it's not unheard of to see like df dx, where you're saying that. You could even do df of x dx, but it's just much less common. So usually if there is function notation, you take the output variable instead, or if there's function notation, you're going to be using that Newtonian notation. You're not going to get dinged for any weird notation on here, but they do like you to know the difference between these two, where the top one means take the derivative with respect to the independent variable, and the bottom one means the derivative of r with respect to x is 2x. And you can take any notes, of course, over on the side. So why don't you go ahead and pause, try the other two, see if you can understand that notation. It's nothing too crazy, and then we'll move on to our lesson. Okay, so hopefully you went through and you said something like, ooh, y prime, that's going to be 3k squared, right? 3 comes down, reduce the power by 1. Or you could say f prime of k equals 3k squared. How do you show taking the derivative? Well, our independent variable is k, so we want to take the derivative of the whole equation with respect to k. So this is going to be ddk of y equals k cubed. And so this is going to become dy dk equals 3k squared. Okay? So we're showing the derivative of the equation called y with respect to k is 3k squared. Now we eventually are going to start changing this variable down here so that it's not always the independent variable we see in the equation. It can be different variables, but I think to start it's just a little easier if we say for now it will always be the same. Okay. And then last but not least, we can do this bottom one. So we're either going to have q prime equals 4t cubed, or you could say g prime of t equals 4t cubed. Either one of those is okay. And then our last part, of course, is we would do d dt of, and you can show these separately too. You can show that you're taking d dt of both sides of the equation. That's also pretty common. So that way you're not dealing with ddk of just one side. So I actually probably tend to use this last one more commonly. But then we get dq dt, look at that cutie, becomes 4t cubed. Nothing too crazy there, but just a nice reminder of that Leibniz versus Newtonian notation. We're going to try to use a little bit more Leibniz today, because yesterday we were much more heavy on the Newtonian. Okay, let's see here. What's our lesson? Given some function f of x, where that could be any function, then what does each limit below find regarding that function? Well, let's see here. I think this first one is our first definition of the derivative. It's our limit definition of the derivative. So this is going to find the derivative function, and our derivative function would be f prime of x. However, this one has taken that same thing but then replaced the x with 0. So now I think this is going to find the derivative at a point, and in particular the point when x equals 0. And so we would notate that as f prime of 0. Right? We're finding a specific slope here versus an equation over here. And last but not least, well, that doesn't really look like it matches anything. Oh, but wait, doesn't it look like they just simplified this down? Yeah, so they might throw that little curveball at you over here, and you'd have to recognize that this still is a definition of the derivative limit, so it's the exact same thing that's over here. It's still going to find f prime of 0. All right. Well, why did we do that? Well, now we're actually going to do this exact same thing up above, but with a function e to the x. And we're going to practice using that limit notation. Now, we should note that we actually can't use the power rule here. You're like, well, wait, if this is the derivative function, can't we like bring x down, e, and then subtract 1 from the power? Well, no, you can't, because our power rule said that we're only allowed to use it if it fits the form of x to some power. And this does not fit that form. That's an exponential equation. We have, so for this one down here, we have 2.718 to the x power. So x is in the power spot. It's not a power function. And so instead, we cannot use the power rule. So when we get to functions where we can't use the power rule, and those functions could be sine of x or natural log of x, none of those will work with the power rule, then we need to go back to our original definition of the derivative, because the limit will always work. So here we go. We're going to find this limit, and I'm going to skip, well, I'm going to skip right to where we evaluate everything. So the limit as h approaches 0, f of x plus h means replace the x with x plus h, minus f of x, well, that's just e to the x, divided by h. Same thing for the second one, the limit as h approaches 0 of e to the 0 plus h minus e to the 0 divided by h. And the last one is going to be, I think, pretty much the exact same thing, right? The limit as h approaches 0 of just e to the h minus e to the 0th divided by h. Well, which of these can we simplify? I think let's maybe start from the far right and then simplify to the left. This one isn't too bad. We have the limit as h approaches 0. Well, maybe we should actually think quickly, and you might not want to write this because I'm going to erase, about what would happen if we replaced all the h's with 0, right? We tried our direct substitution. Well, anything to the 0th is 1. 1 minus 1 is 0 over 0, indeterminate. Ugh, that didn't take us very far. Same thing here. 1 minus 1 is 0 over 0, indeterminate again, bummer. And last but not least, replace the h with 0. E to the x minus itself is 0 over 0, also indeterminate. Okay, they're all indeterminate. And honestly, the definition of the derivative generally turns out to be indeterminate every time. So we have to do more. Okay, well, what's the more here? Let's try actually evaluating each piece. E to the h minus 1 divided by h. We know it's 0 over 0. Can we simplify that anymore? I don't think so. I don't know how to factor it. I don't know what the graph looks like. I think we're going to be stuck there. And I think we'll find the same thing over here. The limit as h approaches 0, e to the h minus 1 divided by h. We can be a little bit sneakier on this first one, though. Let's use one of our properties of exponents here. And that property is splitting apart this addition of powers, because we might remember when you have the same base, then you add the powers together. So when powers are adding together, can't we just take the same base here, right? Minus e to the x divided by h. Well, where do we go from here? I think I noticed something in common to the top. The limit as h approaches 0. Let's factor out that e to the x. That leaves e to the h minus 1 divided by h. And actually, because we're evaluating h at 0, this e to the x is actually a constant here. It's never going to change. And whenever you have a constant with a limit, if nothing's going to be affected with that constant, let's just factor it out to the front. That's going to give us e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Well, drat, all three of these actually end up getting stuck in the exact same spot, right? We have this limit appearing 3 different times from 3, although similar, slightly different limits. So we could actually evaluate them if we knew what this was equal to. Well, the nice part is we're actually going to use our calculator a bit today. So we're going to go ahead and evaluate this limit using our calculator. Now, this limit is a little strange because it uses h. So what we might want to do is, instead of h is just a variable, and that's the only variable in there. So let's maybe treat this as if it was as x approaches 0 of this same function. And as a reminder, you have 2 ways to do this. If you're using your calculator, though, I would suggest maybe looking at a graph and a table as you get really close to 0. Well, the graph of what? Of course, the graph of e to the x minus 1 divided by x. And let's see what happens close to 0. Okay, and so I'm going to pull up my calculator. I have 2 calculators going on here. I already have one equation in here because I'm using that later. So what I'm going to do is turn that one off, and then let's put in this other equation. So I want a fraction, and we're going to, remember on the Inspire you have to use e to the x over here. If you use e down below, it's something different. So it's going to be e to the x, we need to drop down, minus 1 divided by x. Okay, And again, if we substitute in 0 here, we get 0 divided by 0. Looking at the graph, right, it looks to me as we get really close to 0 on both sides, I think we approach 1. So it seems like 1, but what if it's like 1.3 or 1.2, or what if the zoom's not very good? Well, one thing you could do is try a different zoom. You could do menu, window zoom, and then we could use my favorite zoom, which is zoom box. Zoom box lets you move this magnifying glass around, and I would just slightly run your finger over this touchpad till it starts to move around. And I like to pick a corner on the upper left. So what we're literally going to do is draw a box around where I want to zoom in. So I'm just going to go to the left of it here, and then we're going to click that trackpad down once on your calculator, and then draw your finger over to draw a box. And then I'm going to go ahead and just zoom in right on this spot. And then we're like, okay, well that's great, but unfortunately now I can't even tell what that point is. I mean, it looked like it was 1 before. You could trace your graph a little bit over here. However, the other thing we could do is take a quick look at a table, right? And to get a table again, that's Control T. Here's my table, and we're looking at what happens as it approaches 1 over here. Oh, wait, I'm on my wrong graph. I need to switch that. Hold on. There we go. As we approach 0 rather, and it's undefined, so maybe I'll try some other values for my table. As a reminder to do that, menu, table, and I'm going to do edit table settings. Okay, so the table start is fine. I'm going to probably have it start at 0 because that's what I'm interested in. And instead of my independent, I'm going to have it ask me, what do I want to plug in? Well, for my x's here, we want to plug in numbers really close to 0. So let's try slightly bigger than 0 first. Let's do slightly smaller than 0. So let's start with -1. That's easy. Okay, and then let's get closer to 0. So -0.5. Okay, what about -0.1? Okay, what about -0.001? Oh yeah, that's really close to 1 on the left side. Let's go to the right of 0. We'll just do the same thing, but like this. Okay, so just to the right of 0, it's almost 1. Just to the left, it's almost 1. I'm pretty darn convinced that this limit is going to end up being 1. Alright, so as we jump back here, I am again convinced that this limit's going to be equal to 1. I'm going to write that down here. You should have probably recorded your process of what we just did, but this limit is 1. Sweet. Alright, now we can jump back, and we're actually just going to focus on this guy up here. We can jump back and actually evaluate this. So we factored out e to the x, and then we know this limit, so it's going to become e to the x times 1, which is just e to the x. That's wild. And why is it so wild? Because we just came to what is possibly the coolest function in calculus ever, but is definitely the coolest function we've reached so far. Because here are some interesting facts about e to the x. E to the x is its own derivative, because when we did the definition of the derivative applied to e to the x, we got e to the x as the answer. And in fact, it's the only function besides manipulations of e to the x, right? And the constant function, if you take the derivative of 0 at 0. It's the only function in all of math, at least that I'm aware of, where when you take the derivative, it is its own derivative. So e to the x describes the slopes of e to the x. Nothing else is like that, right? I mean, if you thought about x squared, the derivative of x squared is not x squared. The derivative is 2x. It's not its own derivative. E to the x is. And that actually makes your math really easy, too. Anytime you see an e to the x function, you should be excited. You're like, bam, I already know the answer. The other interesting thing about e to the x is it has a rate of change of 1. So up 1 over 1, right? A slope of 1 when x equals 0. And that's because f prime of 0, well, f prime of 0, we're going to use this up here, is e to the 0th, which is 1. And you're like, well, cool, why is that interesting? Well, it's interesting because e to the x, e is a weird number, right? 2.71828, and it goes on for a long time. It's a bizarre number. And it turns out it's the only exponential function that has a rate of change of 1 when x is 0. So all the other exponential functions, 3 to the x, right, or 5 to the x, these nice looking exponential functions, their derivatives are not nice. Okay, so y prime here is also not nice, which means that the derivative of 3 to the x is not 3 to the x. The derivative of 5 to the x is not 5 to the x. E to the x is a, the only exponential function that has a really, I'll say air quotes, nice, end air quotes, derivative of e to the x itself. It's the only one that has itself. And it's the only exponential function that has a nice rate of change at 0. And that is pretty crazy that this really weird number turns out to have a beautiful slope and an easy derivative. And so what we're going to do is we're only going to do derivatives of e to the x, or manipulations of e to the x, for really the next, like, I don't know, 10 or so classes. We're not going to learn these ugly derivatives for, another 10 or so lessons. E to the x is awesome. So how do we use it? Well, we're going to do some practice, and I would suggest on each of these couple practice problems, I think there are 3 of them, that you pause the video, you try them on your own, and then you just check the answers, right? Just skim through, play the video at 2 times speed, something like that. So try it, unpause me whenever you're ready. Equation of the tangent line. Well, we've been doing these. We do these every single day. Strangely, this is shockingly important, and if you haven't picked up on that yet, surprise, tangent lines are important. Make sure, please, that you ask me about them if you are struggling at this point. We've been doing them for 3 or 4 classes now. Generic form of our tangent line. Of course, if we know it's our HK form, HK, the H is given to us. The K is going to be based off of our function, so it's going to be f of 0. And the slope of the tangent is going to be the slope of our function at 0, so f prime of 0. So let's find each of those pieces. I'll do f of 0 in yellow. So f of 0 is just 2 times 0 minus e to the 0th divided by 2. We can get 0 minus 1 over 2, or negative 1/2. Our tangent line then, I'll leave space for the slope. X minus 0, you could just say x, of course, is going to end in a minus 1/2. And let's look at f prime of 0. First, f prime of x. And actually, before I do f prime of x, this is a little bit strange. We haven't talked about e to the x divided by 2. We do know one rule for constants, though, and it's the same for any function that has a constant in front. I'm going to rewrite this. Instead of e to the x divided by 2, I'm going to write it as 1/2 of e to the x. And our rule for constants is that if you have a constant multiplying by a function, you essentially ignore the constant and just do the derivative of the other piece. And we're going to do that here. So f prime of x, the derivative of 2 to the x, well, 2 is a constant, so that stays. This is x to the first. 1 comes down, multiplies by 2, and then we get x to the 0th. But x to the 0th is just 1, and 2 times 1 is 2. So the derivative of 2x is 2. Another way to think about it, the graph of 2x is a linear diagonal function, and it has a slope of 2. Minus 1/2 is a constant. Easy enough. So we just get to focus on e to the x. The derivative of e to the x, that's the easiest derivative ever. It is itself. Cool. Then we look at f prime of 0. 2 minus 1/2 times e to the 0th. 2 minus 1/2 times 1, which is just 2 minus 1/2. And you could say that that is, of course, 1.5. Or we could use 3/2, or you could use 1.5. Pick your favorite. 3/2, I think, takes up the least amount of space, so I'll go with that one. And we have our tangent line. Nothing too terrible. Let's see if we, well, no, let's try B first, and then we'll check to see if we got these right. I'm a big fan of checking it, because then you can go back through and you can kind of self-check your work and see if you made any mistakes, and it's really easy to check in this day and age. The graphing calculator software is everywhere, and it's free. So find the points on the graph of f at which the tangent line is horizontal. So we talked about a problem like this last class. If a tangent line, right, imagine we have some sort of tangent line, and we're going to leave the slope blank, and we'll say x minus a plus f of a. If this tangent line is going to be horizontal, what do we know about the slope? Well, horizontal lines have a slope of 0, right? They are not sloped, they go straight across. So we know this slope has to be 0. What else do we know about tangent lines? Well, we know that this slope right here has to be the same as the slope of the original graph. So what they're really asking here when they say the tangent line is horizontal is they really mean, when is the derivative, when is the slope of f of x equal to 0? Okay, well, I think we can tackle that because we have a formula for the slope of f of x, and they're just saying when will that be 0. So I think we can just set our 0 equal to our slope equation. And then we solve. I'm going to add the 1/2 e to the x to the other side to make it positive. Maybe multiply by 2 here. And how do we undo e to the x? So that's our natural log function. We remember that from Algebra 2 or maybe pre-calculus or maybe summer school, something like that. Those undo each other. The x becomes a regular variable again, and we get x equals the natural log of 4. Now, they said find all points. We found part of a point. Don't forget that if we want to find a full point, we need both an x and a y, and we know it's natural log of 4 comma something. Well, this is a point on f of x, right? They said on the graph of f. So now that we know natural log of 4, we need to go back to f of x up here, or this one if you like this one better, and we need to replace the x's with natural log of 4. So we're going to find f of the natural log of 4, and that's going to be 2 times the natural log of 4. Whoops, need to slide over here. And then it's minus 1/2 e to the natural log of 4. So as we clean this up, 2 ln of 4 minus 1/2 e and natural log undo each other, and the 4 drops down. We get 2 natural log of 4, half of 4 minus 2. And I think this is our y value. So what is our final point? Well, it's maybe not beautiful as you're used to it, but it's better than writing decimals. Generally try to avoid decimals at all costs. If you get something that you can write as a decimal, but you can write it as a natural log or a fraction or something instead, please do that, unless your decimal terminates, unless it stops. So if it's exactly 2.1, go for it. But if it's 2.13131313 forever and ever and ever, then we probably want to say 2 and, whatever that's going to be as a fraction. Okay, so there is that. Let's see if we did it right. I'm going to go ahead and check Desmos. I think I already have this one lined up on Desmos. This was practice problem 1. Here's my graph. As a reminder, we did 2 things. The first thing we did is we wrote a tangent line, and I have this one down here. Was f of 0 negative 0.5? Yes, that's what we got. And f prime of 0 is 1.53 halves? Yes. And here's what our tangent line looks like. Right? I wrote it on Desmos very easily. This is, of course, 3 halves, and this is negative 0.5, but Desmos' notation makes it easy. You'll notice that it bounces off our graph at just one spot over here, right? Just this spot right here. This up here is the x-intercept. Don't let that throw you off. So it bounces off at the correct spot. It's a very beautiful line that's tangent to our graph. The second part, we found where the tangent lines are horizontal. Well, every tangent line that I write over here is going to have a positive slope because the graph has positive derivatives, positive rate of change. The only part where the graph, negative on this side, right? The only spot on this graph where there's a horizontal tangent, which means 0 rate of change, is right at this piece up here, 1.386. So you can go ahead and check that natural log of 4, and I can do that down here if you'd like. Let's get the keyboard. We're going to pull up the function. It's hiding somewhere, miscellaneous maybe. Yep, natural log of 4. 1.386. Is that the same here? 1.386? Yes. Okay. This is natural log of 4. Very exciting. We got the right spot where this graph goes horizontal. So there is our first practice problem. We have 2 more. Here we go. Second one, given y of t equals this bizarre equation, find the following. Also, can you check these on your calculator? Well, we're going to go through this on our calculator in a bit, but again, pause the video, go ahead and try to find these. Hopefully you've unpaused. We have this Leibniz notation thrown at you. dy dt really just means the derivative of y with respect to t. So it's just a fancy way to say the derivative, right? You might have set up this equation by saying take d dt of both sides, something like this. Now, full disclosure, I'm going to erase a bunch of this, so if you're just writing this down, you might want to hold off. This first line is fine, but the rest I'm going to erase. Okay, so d dt of y, well, we just write that as dy dt, so take the derivative of y. Okay, the derivative of y with respect to t is, and then you might be tempted over here to say, ooh, 2t plus 5. The derivative of 2t is 2, the derivative of 5 is 0. Nice. And then the derivative of 3t squared minus 5. The derivative of 3t squared, 2 times 3 is 6. T to the first minus derivative of 5 is 0. And then maybe you even clean this up and you're like, that's just 6t times 2. That's 12t. That's very exciting. When you go over and you try this part, again, I am going to erase a bunch of this, so hang tight. This means take your equation dy dt and evaluate it at t equals 2. Well, since I got 12t, I just want to go through here and say 12 times 2, and that is 24. Except there's one small issue, and the small issue is that up here we have a function with t multiplying by another function with t. And we haven't talked about any of those rules yet. Now, if there was a plus in the middle, then you could take the derivative of each piece individually. We do have a rule for that, but I'm not sure we have a rule for t's multiplying, but maybe we can do what we just did. So let's go ahead and check it. And the way we're going to check it is by going to our calculator, and I'll show you on both of our calculators here. I'm going to turn off my table, Control T. I'm also going to turn off this graph right here, and I'm just going to go back to our main screen. Okay. Main screen. Your calculator has a few functions that not only are you expected to use on the AP exam, you actually have to use on the AP exam. We've discussed some of them. There are actually 4 functions you need to use. The first 2 have to do with solving equations. That's the intersection tool and the zero tool. Those are both on the graphing screen. They help us solve any equation. You're going to get some equations on the AP exam which are not solvable using algebra. So you have to use your graphing calculator to solve. The third function that you're expected to use is the derivative at a point function. So reminding you back to, and you don't need to flip back to this, but going back to what we did at the beginning up here, we said that this first limit, this limit right here, finds the derivative function, it finds an equation. This second one finds the derivative at a point, it finds a particular value. Your calculator, every graphing calculator has this function built in. Whether you're in 83, 84, Inspire, Casio, HP, anything like that, it all has this function. Now, some calculators can actually find equations too. Those are calculators of the CAS variety. You are not expected to do that on the AP exam. The AP exam knows these are out here, and I'll demonstrate this in a second, but you are expected to be able to use your calculator to find the derivative at a point. So what does that look like? Well, on the Inspire, everything you need is hidden in Menu, Menu, Calculus, and then look, derivative at a point. It's number 2 right here. If you have a non-CAS calculator, derivative at a point I think becomes number 1. You won't have the derivative option. I'll demonstrate that in a second, but it's easy enough. You click derivative at a point. What variable do you want to use? Well, jumping back to this screen, the variable that they used in this problem was t, and if you'd like to match it, you can. There's nothing wrong with treating this equation as 2x plus 5 times 3x squared minus 5, and you can use x all the way through. It's the same equation. But if you want to go ahead and use t, we can. So I'll do that one here. So I'm going to go ahead and use t. So I'll delete this one out. We're going to say we're going to use the variable t because that sounds fun. And then value is, what value do you want to plug in to your derivative? Well, I want to plug in 2. They said when t equals 2. And then what derivative? Well, this gives you the first, second, or nth derivative. We're going to ignore the rest of those. Technically, those aren't even things the AP exam asks you to do. They might become useful later, but for now, just the first derivative. Hit OK, and it says, cool, what should we find the derivative of and then evaluate it at t equals 2? Notice they use that Leibniz notation here. Well, our equation had a couple sets of parentheses, right? It was, I don't even remember it, unfortunately, so I'm probably going to have to go back. Notice we're using t here, not x. So there was something with a 2t, and there was something with a 3t squared, and there was a minus 5 over here. And jumping back, that is unfortunate, poor memory. 2t plus 5, 3t squared minus 5. Okay, so I just need a plus 5. Plus 5. Here's all this, and I'm going to hit enter, and it'll say your answer is 122. Well, your calculator's not wrong. Your calculator is going to do the right stuff. So if I jump back over here, my calculator is telling me that dy dt evaluated at t equals 2 is 122. We got 24. I think that means we made a small mistake here. So this is where I'm going back to erase a bunch of things, and we need to have that quick talk about other rules. At this point in time, we don't have a way to find the derivative of two functions. And when I mean functions, I mean two expressions that each have a variable in them multiplying together. If there's multiplication between, you have to find a way to combine them so that there isn't multiplication in between. And I think what we can do here is just a little bit of algebra. Let's go ahead and multiply all of this out. Let's take 2t plus 5 and multiply it times 3t squared minus 5. 2t times 3t squared is going to be 6t cubed. We'll do the squared term next. That's 15t squared. That was right here, right? We've already done this one. Then I'm going to go ahead and tackle, I think probably 2t times negative 5 is negative 10t, and we'll finish off with negative 25. This is the same as the original equation, just expanded out. And now you'll notice that every term is separated by addition or subtraction, and every term that I just circled only has one instance of t. There's no two different terms multiplying. Now that we're here, I think now dy dt becomes much easier. 3 times 6 is 18t squared. That's not breaking any rules. 30t minus 10, and then the 25 just goes to 0, so I don't really care about that. And we end up here. Very exciting. If you wanted, you could go further, of course. You could say, well, we're going to be plugging something in, so let's maybe at least divide out a 2 from everything. This is 9t squared plus 15t minus 5. Maybe that's going to be easier when we evaluated at 2, right? Just dividing everything by 2. But let's get to it. So dy dt evaluated at 2 means we're going to do 2 times 9 by 2 squared plus 15 times 2 minus 5. And as we continue down, this is 4 times 9, that's 36, plus 30 minus 5. And 36 and 30, well, let's see, that's going to be 66 minus 5 is 61. 2 times 61, 122. Our calculator was right. So again, the calculator shockingly did not lie to us. In fact, the calculator will always be correct, and any mistakes that happen on there will probably be user error. Couple more things to note. First, how do you do this on the 84 or the 83, because that's probably worthwhile knowing, and then what are a couple other tricks your calculator can do for you? Well, it's very, very similar, but we're going to access the math menu on the main screen. We're going to go math, and then you're going to go down until you get to n derivative, the nth derivative. Right? Actually, the n stands for numerical derivative. It's going to find the derivative and give you a number as an answer. So I want the numerical derivative, and if your calculator is updated, it should give you a screen that looks like this. If you don't get this screen, just come talk to me and I'll update your calculator to the newest operating system. This is for the TI-84. The TI-83 cannot update to this screen. There's different syntax. We can talk differently later on, but here we go. dd what? Let's use ddx this time. You could use t, but your calculator defaults to x, so a lot of times it's easier. And then we'll do the same equation. So we have 2x, I think it was plus 5, parentheses, and then we had 3x squared minus 5. We're going to tap that right arrow. And actually, I think I'm missing a set of parentheses too. Let's double check over here. I have one parenthesis here, yeah, and you'll notice that there's small parentheses, small parentheses. I'm going to go ahead and throw another parenthesis in the end right here. There we go. Now I think we have enough parentheses. Good. Evaluated at x equals what? X equals 2 and 122. You'll notice the calculator says 122.000006, and that's because the calculator doesn't know calculus. It's not actually taking the derivative and plugging in 2. What it's doing is it's using those limit definitions. It's actually using the symmetric definition of the derivative that we covered last class. It's basically graphing our original equation and then picking 2 points really, really close, one just slightly below, one slightly above, and then calculating the slope using the slope formula for this function. And if it doesn't pick numbers close enough, then it's going to get some sort of decimal. So you're going to have to get used to, if you have an 83 or 84, realizing that this means 122. These extra decimals are just the calculator's error calculating that. So this is the exact derivative of 122. Two other things about your calculator, and I'm going to jump back to the Inspire, but the 83, 84 works the same way. I did graph this function, so let's see, I'm going to go back to a standard window really quickly. I did graph this function up here, and it's right here, and I used x because your calculator will only take x as an input on your graphing screen, f1 of x, and f1 of x is important. That's the name of my graph. Oops, and I should probably hit the check mark. There's my graph. Now, what I'm going to do is I'm actually going to go back to my other screen, my calculating screen, and I'm going to go through this process again when we did the derivative, but I'm going to do menu, calculus, again, derivative at a point. What variable? I'm going to use x this time, because on my graphing screen I used x, and I'm going to use the equation that I typed into the graphing screen. So if you already have this equation graphed, and you remember the name of the equation, mine was called f, and as soon as I type 1, you'll see it turn bold, f1 of x, then that might save you some time. It says find the derivative of whatever's in the graphing screen in f1 at x equals 2, and you'll get that 122 again. Last but not least, I am running a CAS simulator up here, so I wanted to show you what the derivative looks like on a CAS calculator. So menu, calculus, derivative, it's number 1 this time, so I did 1. You'll notice it doesn't have the evaluated at part, and I'll again do ddx. I'm going to be very lazy, I don't want to type it out, so I'm going to do f1 of x right here. Again, it's just going to type that same equation. But this cool CAS, computer algebraic system, is actually going to go through and find the derivative for you. CAS systems can find equations as answers. Non-CAS systems, like just the plain old CX or regular Inspire 8384, can only find numerical answers. So what this gives for us then is a nice way to check our derivative. But before those of you that don't have a CAS are dismayed about your choice in calculator, it's fine. The AP exam, of course, knows that CAS calculators are out there. There is never going to be a situation where being able to find the derivative is a big advantage for you, right? There's never going to be a situation where you need to go through and using a CAS calculator will be easier to find the derivative than doing it by hand. Either all the derivatives will be on the non-calculator active section, or there'll be a way to do it using the non-CAS calculator. So, thanks for joining my TED Talk for that. Let's get back to our problems here. Okay, we are on, there we go, 2. Okay, now we're on 3. Cool. Given the function below a and b. All right, go ahead and try that on your own, and then we'll discuss. Hopefully you are back. If you are back, then you might have realized there's going to be an issue with this problem as well. The one thing you can't do, and you can write this up above, I'm going to show x prime of t here, is you are not allowed to take the derivative of each one individually. 4t cubed minus 3t squared divided by 2t. That is a no-no. Why is it a no-no? Well, it's really the same thing that we just talked about before, right? Up above, we had two functions, and again, I'm using function loosely here. We had two expressions where each expression had a variable and they were multiplying. Well, here you have two expressions and they're separated by division. And we also don't have a rule that says you're allowed to take the derivative of each piece separately. In fact, you can't take the derivative of each piece separately and still get the right answer. So how do we do it? Well, there's a couple ways that you can simplify this problem before you take the derivative, and you can use whatever space you would like for this. I'll show you both methods because I find there's a few of them, but I find that students are drawn to one method over another, and like 50% of my students use one way, the other 50% use the other, and there's no real perfect way that I think is the best. So one way that we can tackle this, and I'll show this problem twice t to the fourth minus t cubed over t squared. One way we can do this is by realizing that there's just a single term in the denominator, so we can split this fraction up. So when we split it up, t to the fourth divided by the common denominator minus t cubed divided by the common denominator. Realizing, of course, that with this common denominator you could put it back together and end up where we started. Once we've done that, simplifying becomes way easier. T to the fourth over t squared is just t squared, and this one just becomes t. And that is way easy to take the derivative of. Another way you can do it, and this is also a popular method, is you could rewrite this as t to the fourth minus t cubed times, and then we're just going to bring this guy up. Notice I grouped the top in parentheses, the numerator in parentheses. We do need to do that, and we're going to multiply by t to the negative second, because whenever we change a term's location in a fraction, you have to change your exponent sign. Once we're here, distribute. And now we come into the idea of having the same base, and what do you do with the same base? Well, you add the exponents. So we end up with 4 plus negative 2, which is 2, and 3 plus negative 2, which is 1. And we get the same thing. And it's really the same amount of work. It's whichever one appeals to you more. So either of those are fine, but regardless, we do need to simplify it down. So now we have two terms that each have a variable that are separated by addition or subtraction instead of division. The rest of this becomes way easier. We have dx dt over here, which means take the derivative of this function, or rather find the derivative of this function. That's just going to be 2t minus, this is t to the first, the 1 comes down, and we get t to the 0th, which is just 1, so 2t minus 1. Find x prime of 3. Well, x prime of 3 is going to be the derivative, which we found over here, evaluated at 3. So x prime of 3 is going to be 6 minus 1, which is 5. It's maybe not a bad idea to check that on your graphing calculator just to make sure you did everything right. However, I wanted to quickly show you how you could check this on Desmos in case you forget your graphing calculator, because Desmos does the same thing as a non-CAS graphing calculator. So here is Desmos. I'm just going to look at practice problem 3 here. I typed this in using function notation, and you do have to use function notation. Desmos prefers if you use f or g of x as opposed to anything else. Here's the graph in case you're curious, but you don't really need that. If you type in g prime of x, Desmos is not a CAS calculator. It's not going to tell you the equation. It does give you the graph of the equation. You can see that this is a linear graph. Remember, it wasn't our g prime of x 2x minus 1. It starts at -1 right here, and then goes up 2 over 1, up 2 over 1. It does match up with this, so you could check the graph type if you wanted, but g prime of x isn't going to help us too much. However, if you type in g prime of 3, the graph, the derivative evaluated at an input, it does give us an answer of 5, which matches our 5 as well. So again, to use your derivatives on Desmos, g of x, g prime of whatever, where the prime is just the apostrophe on your keyboard, and it's a nice way to check derivatives if you don't have a calculator. Just about done for today. I think the only thing that we have left then is the last part, which is actually the very first part of the title, which is higher order derivatives. This part, though, is pretty easy. So far, we've only taken the derivative of the function to find its derivative function f prime of x. But the derivative, well, okay, let's go back. The derivative function tells us about the instantaneous rate of change of f of x. It tells us the derivative of f of x. It tells us the slopes of f of x. However, as we just saw on Desmos on the previous screen, we could graph f prime of x, right? I graphed this on Desmos. This, of course, is also a function. I mean, it's the derivative, but it is still a function. It was something we were able to graph. And so, couldn't we take the derivative of that? Well, of course we could. So, derivatives can be taken as many times as you would like. And they're notated in any different number of ways. You have your fn of x, which would be an example like f prime of x, right? You have your y, which would be like just y prime. Both of those are Newtonian notations. And then this one's going to be a little different. dny over dxn. We've seen one of these before. We've seen one of these where n is 1, right? Because you don't need to write those exponents, so it becomes dy dx. So we've seen that once, that's our Leibniz notation, but those n's are a little bit weird, and I'll show you where they come from in just a second too. What we have here to finish off then are two equations, one here, one over here, and they're asking us to find a lot of derivatives. First, second, third, fourth, and fifth derivatives of all of these equations. Let's start with our polynomial over here. I think it'll be a little nicer. So let's go ahead and do our first derivative. Well, the first derivative, Newtonian-wise, is just going to be, let's see, f prime of x. Let's maybe just do the Newtonian all the way down. 3 times 3 is 27, isn't it? No, 3 times, yeah. No, 3 times 3 is 9. Whoops, those are exponents. So we get 9x squared minus 5, right? Derivative of 12 is 0. How do we notate the second derivative? Well, that's just going to be f double prime. And that's when we say f double prime, we put those two little tally marks there because that's really what they are. Kind of. Yeah, I think you'll see they're not quite tally marks in a second. F double prime, not f prime prime, though I do have some students that say that, and it always makes me laugh. We say this is f double prime, and then we take the derivative of the function above. 2 times 9 is 18, x to the first power, derivative of 5 becomes 0. All right, f triple prime, or the third derivative. Derivative of 18x is just 18. The fourth derivative, things get a little bit strange. You have a couple ways to notate this. Sometimes you'll see the fourth derivative written like this. And then you might realize that, oh wait, these aren't tally marks. These are actually Roman numerals, right? This is our Roman numeral 1, 2, 3, and this is the fourth Roman numeral. So the fourth derivative of x, right? Derivative of 18 is just 0, I think. And really, anytime after the fourth derivative, you could argue that someone would do a 5, but it's really uncommon. A lot of times they'll just put a 5 in parentheses, and that means the fifth derivative. You could do that for all of these. You could even say the third derivative, whoops, the third derivative, something like that. But yeah, once we get beyond 3, really, even to 4, they'll usually just put parentheses and the number in there. So the fifth derivative of x, well, this is 0. The derivative of 0 is itself. It's that constant function. And I think you can tell that if we kept doing derivatives, nothing much is going to happen here. 0 all the way down. Well, what does it look like for Leibniz notation? I think it's important to show 2 steps on each of these, and the first is going to be what we're taking the derivative of. So we're going to go ahead and instead of f of x, let's just use y. I think it's going to make a little more sense here. So we're going to take the derivative of y, and we're also going to take the derivative of 3x cubed minus 5x plus 12. Well, the derivative of y is dy dx. That is the derivative of y with respect to x. The derivative of the right side, we already did that once. We can skip forward quickly. It ends up being here. Nice. Let's do that same process again. So we called this y, and we started by doing the derivative of that. So this one, we're going to take the derivative of the equation from before of dy dx, which means we're going to take the derivative of 9x squared minus 5, taking the derivative of the derivative. Now, if you think of this as fraction multiplication, and it's not really, and I think a lot of professional mathematicians would probably wince at me saying that, but it's an easy way to remember this. If you think of this as fraction multiplication, you have d times itself, which is going to become d squared. There's nothing times the y, so the y stays the same. On the bottom, you have dx times itself, which is going to be dx squared. However, it's never written like that. They don't put in parentheses. We just write it as dx squared. Technically, the squared should be around the whole thing, but this is our shortcut notation, and this means the second derivative of y with respect to x twice. And we end up with 18x. Same idea as we continue down. So our third derivative, I need to take the derivative, that stays the same every time, take the derivative of this second derivative, and so of course I need to take the derivative of 18x. We continue on through, think again fraction multiplication as we're moving on through. D times d squared is going to become d cubed, the y stays the same, divided by dx, well this was originally a 2 up here, hard to see, sorry, and we're multiplying by a third one, so it becomes dx cubed, equals just 18. And of course our fourth derivative, I think we see the pattern now, right? The fourth derivative is going to be 0, and the fifth derivative is also 0. If you're not sure where those little exponents go, no one's going to take off points for it, but just set it up the way that I did. Say, take the derivative of this guy and then multiply straight across, and it'll help you keep straight where those exponents go in your problem. All right? No, we have one more to do then. We have our Newtonian and Leibniz notation. This time we have this e to the t with a constant in front. Remember, the constant isn't going to change anything. We're going to do this one faster. So, first derivative, y prime, maybe I should say of t here, y prime of t equals, well, the derivative of 3t is just 3. The 2 is a constant, and the derivative of e to the t, that's the easiest derivative ever because it's itself. It's the coolest function. Don't forget it. Leibniz notation, the derivative with respect to t, right? It's d dt of each side is going to be 3 plus 2e to the t. Let's continue down. My second derivative, well, derivative of 3 is 0, 2 is a constant, e to the t stays the same. So in fact, we probably could have simplified it, and I will do it over here. Right? Our second derivative, don't forget those squares, is just going to be 2e to the t. All right, what about that third derivative? Well, 2 is a constant, e to the t is itself, easy enough. Third derivative, same thing here. We end up with itself. Well, I think actually we could probably predict what the rest of these are. It looks like it's going to be 2e to the t all the way down. So my fourth derivative, I'll write it like this time, is going to be 2e to the t. And of course our fifth derivative, just skipping around here like so, is going to again be 2e to the t. And in fact, it has an infinite number of function derivatives that never become constant because e to the t is just that cool. Now, we took the derivative of all of these, but we didn't really say what they described. So what do you think they tell us about the function? Because they all have to tell us about f of x. The whole point of taking derivatives is to better understand f of x. Well, we know that f prime of x tells us about the slope of x. It's the derivative that describes the slope. So what does f double prime tell us about f prime of x? Maybe look at a quick example. Let's say that f of x is x squared. F prime of x equals 2x means that at every x value, the slope of x squared is changing by a rate of 2x. When x is 3, this becomes 6, so it tells us that at 3, x squared is changing at a rate of up 6 over 1. So this 2x tells us about the rate of change of f of x. Well, if I went to f prime equals 2x, and then we found f double prime, the derivative of 2x is 2, well, they have the same relationship. F double prime is telling us about the change in the slope of f prime. So it's telling us how fast f prime is changing. It's saying at every x value, the first derivative is changing at a rate of up 2 over 1. But could we bring that back to f of x? Well, this is telling us the rate of change of the rate of change. So it's telling us how fast the slope of x squared is changing. So this is the slope of x squared, and then this is going to be the rate of change of the slope of x squared. Could we go further? Of course we could. We could say f triple prime of x, which in this case is 0, tells us that f double prime isn't changing. Or you could say that the rate of change of the slope of f prime is 0. Or you could go even further and you could say the rate of change of the rate of change of the slope of x squared is 0. And you could continue all the way down. So what that really means then is with our exponential function, the rate of change is always changing all the way down. However, for these polynomials that we saw over here, eventually the rate of change stays constant. And you actually touch on this shockingly in Algebra 1. You have this third power, and they tell you that the rate of change, or the constant difference, becomes constant if you look at the patterns of the third slopes. And if it was x squared becomes constant, right? We saw this down here. X squared becomes constant if you look at the second common difference, and x becomes constant if you, or x to the first becomes constant if you look at the first common differences. There's a pattern there. All that really is derivatives, but explained in a different way. Now, do you need to be perfect on this section? No. Actually, our last unit for this semester, topic 4, is going to really focus in on that. For now, we're just really introducing the rules, but it's always nice to give some context. I get those students that say, but wait, when are we going to use this? Well, ultimately, calculus has two main ideas. Limits builds everything up, but I wouldn't necessarily call that the hugest of ideas. Really, we focus on derivatives and integrals. Derivatives is essentially the science of the rate of change, the science of slopes, if you want, because it's extremely important to see or to be able to measure how fast something is changing to make predictions. Right? How fast is the stock market changing? How fast is a river flowing? You can start to have applications to physics, to anything really out there that has some sort of change. And so that's what our main focus is going to be on this first semester, with these next two topics, topic 2 and topic 3, really grounding you or getting you comfortable with all of our rules. And then the fourth topic is going to be how do we apply those rules. So thanks for hanging in with me, and I am excited to see your success. Don't forget you do have a few independent practice problems this evening.